Hello everyone, welcome to the channel TOC Gate. In this video, we'll see the conversion of regular grammar to finite automata. So in the previous few lectures, we have seen the conversion of the grammar to the language and the conversion of the language to the grammar. In this one, we'll focus on the conversion of the regular grammar to finite automata. Clear? So first of all, let's try to find out that what is a regular grammar. Of course, we have already discussed this in the previous lecture about the Chomsky classification of grammars. So in that one, we know that in a regular grammar, in every production rule, there should be exactly one variable onto the left hand side of every production, and onto the right hand side, there can be any number of terminals. There can be any number of terminals. And if on the right hand side there is a variable, this variable should be either on the extreme left position or onto the extreme right position. Clear? That means suppose I have a production rule as say s tends to, I have a. Okay, so we have a variable onto the left hand side, a single variable. Onto the right hand side also we have a single variable, but this variable should appear onto the extreme left position or onto the extreme right position. So I can have this way also s tends to a, or I can have this way also s tends to a, b, a. That means any number of terminals are possible and then followed by a variable, or a variable followed by any number of terminals. So we can have this way also s tends to a, say a, b, a, and so on. Clear? So all these type of production rules are possible in a regular grammar. But if you have production rules such as s tends to a, capital A, small b, now this is not a regular grammar. Why? Because here we have a variable onto the right hand side, a single variable, but this variable is appearing neither onto the extreme left position nor onto the extreme right position. Therefore, this is not a regular grammar, and all these are regular grammars. Clear? So if you see here, we have taken 4 different grammars, G1, G2, G3 and G4, and all of these grammars are regular grammars. You see here in this production rule, we have s tends to as. So s tends to as means left hand side single variable, right hand side single terminal followed by a single variable onto the extreme right position. Again single terminal and a single variable onto the extreme right position. Clear? Here also one variable on the extreme right position, one variable extreme right, and so on. So all these grammars are basically the regular grammars. Okay. Also, we have seen that a regular grammar is of two kinds. Regular grammar is of two kinds. One is called as a left linear grammar. One is called as a right linear grammar. What is left and what is right? If onto the right hand side, if the variable is appearing on the extreme right position, that will be called as a right linear grammar. If the variable is appearing onto the extreme left position, that will be called as a left linear grammar. So this one will be your left linear grammar. Why? Because the variable is appearing onto the extreme left position, and you can say this one will be your right linear grammar. Why? Because the variable is appearing onto the extreme right position. Clear? So I have taken 4 grammars here, and then I'll show you how to convert these grammars into equivalent finite automata. Clear? So the conversion of this grammar to finite automata is quite simple. It's very easy. So in this one, if you see, we have 2 variables s and a. So s and a means in the equivalent finite automata we'll get 2 different states. Okay, so let's see how we do this one. So first of all, because we know that we have to start from the start variable only. Okay, so what we'll do, we'll start from the start variable. So this start variable will become my initial state. Okay, so s, now s derives as. What does that mean? That means with a, I'm moving on to the state s. So what will I do? I'll just simply make a self loop of a. That means s tends to as. Clear? Okay, again it says s tends to ba. That means on s, if you apply b input alphabet, you'll move on to the state a. So I'll make a state a and connect this with a with the input alphabet b. That means from s, if you apply b, you'll move on to the state a. So s tends to b a, s tends to a s. Clear? Okay, next one is A tends to CA. What does that mean? That means if you apply C on A, you'll reach on to the A only. That means it is a self loop. Clear? And then it says A tends to epsilon. What does that mean? If epsilon is getting derived from any variable, that means that variable is a final state. So this becomes my final state, and this is the required finite automata for this particular grammar. So you see how simple this one is. Clear? Okay, now let's make things a little bit complex here. So I have in this one 3 variables. Let's see how we can convert this one into a equivalent finite automata. So let's see how we do this one. So first of all, we'll start from the start variable. So s becomes my initial state. Then s tends to 0s. That means it is a self loop. Then s tends to 1s. Again, it's a self loop, as I'll just put a comma here. S tends to 1s. Again, it says s tends to 0a. That means if you apply 0 on s, you'll reach on to a state a. So I'll take a state a and then connect this with 0. S tends to 0a. So s tends to 0s, s tends to 1s, s tends to 0a. Clear? Now move on to the a. A tends to 1b. That means I'll take one more variable b, and a tends to 1b. So a tends to 1b, and then it says b tends to null. That means b is a final state. So I'll just simply make b as a final state, and this is my required finite automata for this particular grammar. Okay, now let's move on to the third one. Third one, I have s tends to 0a 1b, a tends to 0a 1a 0, and then b tends to 0b 1b and 1. So let's see how we do this one. So again, I'll start from the start variable, that is s. Then it says s tends to 0a. That means with 0, I'll move on to the state a. So s tends to 0a. Then it says s tends to 1b. So I'll take a state as b. So s tends to 1b. Then it says a tends to 0a. That means 0 self loop. Again it says a tends to 1a. That means 1 self loop. And then it says a tends to 0. So what will I do? In this one I don't have any variables. So what will I do? I'll just simply take a final state here and represent this with the help of a epsilon, and then connect this with 0. Okay, now come on to the b. B says b tends to 0b. That means it is a self loop, 0b. Then it says b tends to 1b. That means it's a self loop, 1b. Then it says b tends to 1. That means it is a movement to the final state with 1. So this is your required finite automata for this particular grammar. Okay, now let's see the fourth one. So fourth one, again I have s tends to 0s and 1s. So I'll just start from the start symbol, that is my initial state. So s tends to 0s, that means it is a self loop of 0. 1s, that means a self loop of 1. Then 1010a. So what will I do? First input alphabet is 1. So I'll apply 1 and I'll reach on to a state, say what is left, 010a. So I'll just write 010a. Now the next input alphabet is 0. So here I'll apply 0 and then I'll move on to a new state. That means it is 10a. Now next alphabet is 1. So from here I'll apply 1 and reach on to a state 0a. Clear? Now next alphabet is 0. So from here I'll move with 0 to a state a. Clear? So this is done for s. Now come on to a. So a, it is 0a and 1a. That means it is a self loop, 0 comma 1, and a tends to epsilon. That means a is a final state. Clear? So this is the required finite automata for this particular grammar. So let's see one more example here. We have this G5, and in G5 we have s tends to 001s/10a and a tends to 101a/0/1. So again we'll follow the same approach. So first state is s, that is my initial state. So from s the input applied is 0. So I'll apply 0 and then where I'll reach on to 01s. Clear? Now next alphabet is 0. So here I'll apply 0 and reach on to the state 1s. And the next alphabet is 1. So from here I'll go to directly s with 1. Now we have s tends to 1 0 a. So s tends to 1 0 a means when you apply 1 you will move on to 0 a. That means apply 1 and move on to state 0 a, and then the next alphabet is 0, so apply 0 and reach on to the state a. Now come on to the a says it is 101 a. That means 1 applied and it will reach on to 01 a, 01 a, and then next alphabet is 0, so apply 0 and reach on to 1 a, and then next alphabet is 1 and it is reaching on to a. So from here I'll come on to a with 1. Clear? And then it says a tends to 0, a tends to 1. That means here it will be a final state. So I'll just make a final state here. That is my epsilon, and then connect this with a with 0 and 1. So this is the required finite automata for this particular grammar. Clear? So that is all. Thank you so much.